Hello, friend. Welcome to Science for Sleep. Whether you have returned tonight, or you are finding this quiet place for the first time, this is a calm space to slow down, learn something gentle, and let the day slowly fall away. Tonight, we are going to Pisa, a small city in Tuscany, in central Italy. There, on a green lawn in the Piazza dei Miracoli, stands one of the most famous buildings on Earth. The Leaning Tower of Pisa rises in pale white marble beside the city's cathedral. It is not the tallest tower in the world. It is not the largest. It is not covered in gold or glass or modern steel. And yet, it is one of the few buildings that nearly everyone can recognize from a single glance. The reason is simple. It looks like it should be falling. The tower stands about 56 meters high on its higher side, which is about the height of an 18-story building. It weighs roughly 14,000 tons. It has 8 levels, including the bell chamber at the top, and its round body is wrapped in rows of arches and slender columns. But the detail people notice first is not the marble. It is the tilt. The whole tower leans to one side, as if gravity has been gently pulling it away from the sky for centuries. When you see it in a photograph, the eye almost wants to correct it. The horizon may be straight. The cathedral beside it may be steady. The people on the lawn may be standing upright. But the tower seems to drift out of place, held in a long, quiet moment between balance and collapse. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. What makes the tower so strange is not only that it leans. Many things lean. Old fence posts lean after years of rain. Trees lean toward sunlight. A person can lean to one side while standing still, shifting weight from one foot to the other. The deeper surprise is that the Tower of Pisa has leaned for more than 800 years. Construction began in 1173. That means the tower was already part of the city before the printing press, before telescopes, before modern physics, and long before anyone could measure tiny movements with electronic sensors. For century after century, people walked past it. Rain fell on its stone. Bells rang from its upper chamber. Earthquakes shook the region. The ground slowly changed beneath it, and still, the tower remained. A leaning object does not fall simply because it is not straight. It falls when its weight shifts too far beyond the area supporting it. You can picture this by standing with your feet flat on the floor and slowly leaning to one side. For a while, you can hold yourself there. Your body may feel uneven, but you do not fall because your weight still lands over your feet. Lean a little farther, and there comes a point where your foot can no longer catch you. The body tips and balance is lost. The Tower of Pisa lives near that same idea, only in stone, soil, and time. Its weight does not simply press downward. Because the tower leans, that weight also creates a turning force, a slow pull that tries to rotate the structure farther toward the ground. Every block of marble, every column, every bell, and every step in the spiral staircase adds to that quiet pressure. Yet the tower has not crossed the final boundary. It stands because the invisible line of its weight still passes through the base closely enough to be held. That is the first gentle puzzle of Pisa. The tower appears to be an accident happening in slow motion, but it is also a lesson in balance. It shows how something can look impossible from the outside while still obeying the patient rules of physics. The marble tower is the part we can see. The lean is the part we remember. But the true beginning of the story is lower down, beneath the grass, beneath the paving stones, beneath the shallow foundation, where the ground itself was never as firm as it seemed. Beneath that quiet lean, the tower began as something very ordinary for its time. Not ordinary in beauty, but ordinary in purpose. It was meant to be a bell tower. In Italian, a bell tower is called a campanile. The word comes from campana, meaning bell. A campanile did not need to touch the church beside it. Its job was to lift heavy bells high enough for their sound to travel over rooftops, streets, markets, and fields. In medieval Pisa, that sound mattered. Bells marked prayer. They marked time. They marked feast days, warnings, funerals, and the steady rhythm of public life. So when construction began in 1173, the people of Pisa were not trying to build a famous leaning monument. They were adding the final great piece to a sacred complex already rising on the north side of the city. The tower stood in what is now called the Piazza dei Miracoli, or Square of Miracles. Nearby was the cathedral, a grand marble church begun more than a century earlier, in 1063. A little farther away stood the baptistry, the round building used for baptisms, whose construction began in 1152. Together, the cathedral, baptistry, cemetery, and bell tower formed one of the most beautiful religious spaces in Europe. The tower was meant to complete that scene. It was meant to stand near the cathedral like a column of music, a white stone instrument holding bells above the grass. Seen from a distance, it must have looked strong from the very beginning. Its lower level was built from pale marble. Its round base was surrounded by blind arches, which are arches set into the wall for decoration rather than open passage. Above that, rows of slender columns would eventually circle the tower like rings. Each level looked light and graceful, even though the structure itself was enormously heavy. The stone gave an impression of order. Arch above arch, column beside column, a round shape rising neatly from the lawn. But the strength people could see was only part of the story. Stone can look permanent, even when the ground below it is quietly shifting. A tower can be carefully carved and still depend on something much softer than marble. Every building begins with a hidden agreement between weight and earth. The walls press down. The foundation spreads that pressure. The ground pushes back. When those forces match well, the building rests. When they do not, the building begins to move. At Pisa, the visible design was beautiful, but the hidden agreement was poor. The tower was built on a flat piece of ground near the Arno River and close to the old edges of marshland and coastal plain. For thousands of years, water had helped shape that land. Rivers carried sand, silt, clay, and tiny shells across the low plain. Floods laid down thin layers. Wet seasons softened them. Dry seasons pressed them tighter. By the time medieval builders arrived, the surface could seem calm and solid. Grass grew there, people walked there. The cathedral already stood nearby, but below the surface were layers that did not behave like firm rock. They behaved more like a heavy, damp cushion. This is why the tower's first weakness was not dramatic. There was no crack splitting the marble on the first day. No sudden failure. No loud warning. The problem was quiet. The tower's round body began pressing thousands of tons into soil that could compress unevenly. Compression simply means being squeezed smaller under weight. Clay can compress more than stone. Wet sediment can shift more than dry gravel. And if one side of the ground compresses even a little more than the other, a tall structure above it begins to tilt. That is the strange softness at the heart of Pisa. The tower did not start as a mistake in the sky. It began as a beautiful plan placed on uncertain earth. From above, the builders saw marble, arches, bells, and sacred space. From below, the ground received a weight it could not hold evenly. And before the tower could become the landmark the world remembers, the soil beneath it had already begun to decide its future. The ground beneath Pisa had been telling its own slow story long before the first stones of the tower were placed. The city sits on a low plain in Tuscany, not far from the Ligurian Sea. The Arno River runs through Pisa, carrying water westward from the hills and mountains of central Italy. Over thousands of years, that river helped build the land beneath the city. It carried tiny grains of sand. It carried silt, which is finer than sand but rougher than clay. It carried clay, which is made of particles so small they can stay floating in water for a long time. When floods spread across the plain, those materials settled out in thin layers. One season might leave sand, another might leave soft mud. A quieter stretch of water might leave fine clay. Closer to the coast, shells and marine sediments could become mixed into the ground as old shorelines shifted. This kind of ground is called alluvial soil. Alluvial simply means it was laid down by moving water. It is not one solid piece of stone. It is more like a layered record of floods, river channels, marshes, and old wet ground. That kind of soil can hold a city. It can hold streets, houses, churches, and fields. But it does not always hold heavy weight evenly. Beneath the Leaning Tower, the layers were not all the same. Some were sandy, some were clay-rich, some contained shells, some held more water than others. Each layer squeezed in its own way when the tower pressed down on it. Sand grains are larger, and when they are packed tightly, they can carry weight fairly well. Clay is different. Clay particles are flat and tiny, and water can sit between them. When heavy weight presses down on wet clay, the water slowly moves out, and the clay layer becomes thinner. This does not always happen quickly. Sometimes it takes years. Sometimes it takes decades. Sometimes the change is so slow that people standing above it cannot see it happening at all. But a tall tower can feel even a small change. If one side sinks just a few centimeters more than the other, the top moves much farther. A tiny difference below becomes a large lean above. You can picture it by placing a heavy book on a thick mattress. If the mattress is perfectly even, the book may settle straight down. But if one side of the mattress is softer, or if one corner is pressed a little deeper, the whole book begins to tilt. The book itself may be strong, its cover may be firm, its pages may be square, but the surface beneath it decides how it rests. The tower in Pisa was like that, only far heavier and far taller. Its marble walls and columns were not floating above the problem. Every stone sent weight downward. That weight passed into the foundation, then into the soil, then into the softer layers below. The tower weighed thousands of tons, and the ground had to answer that weight every moment of every day. At first, the difference may have seemed small. A slight settling, a tiny shift, a barely visible change in the line of the walls. But soil does not need to fail all at once to change a building. It can move by compression. It can move as water slowly drains. It can move as one buried layer squeezes more than the layer beside it. This is why the tower's lean feels so strange and so natural at the same time. Nothing magical had to happen. The tower simply stood on ground that had been built by water, not by rock. Its base rested over a quiet mixture of river history and coastal memory. Clay, sand, shells, silt, and groundwater all sat beneath the white marble like a hidden, uneven mattress. That softness did not make collapse certain. Many buildings survive on soft ground when their foundations are wide enough, deep enough, or carefully designed for the soil below. The danger at Pisa came from the meeting of two things: a heavy stone tower above, and a foundation beneath it that did not reach deeply enough into firmer ground. The earth could bend slightly under the weight, and because the tower was so tall, even slight bending below could begin to write itself into the sky. The softness beneath Pisa would not have mattered as much if the tower had been anchored deeply into the ground. A tall stone structure needs more than strong walls. It needs a base that can spread its weight and reach soil that can resist movement. At Pisa, that base was surprisingly shallow. The foundation of the tower was only about 3 meters deep. That is roughly the height of a small room. For an ordinary building, 3 meters can be meaningful. But for a marble bell tower rising more than 50 meters into the air, it was very little. The tower would eventually stand about 56 meters high on its taller side. That means the foundation reached only a small fraction of the tower's total height into the earth. You can picture a tall candle set into a shallow dish. The candle may stand upright at first. Its shape may look clean and balanced. But if the dish rests on something soft, the candle has very little grip when the base begins to sink unevenly. The Tower of Pisa had the beauty of marble above, but below it, the structure did not reach far enough to escape the soft layers near the surface. Its foundation was circular, matching the round body of the tower. The tower itself was about 15 to 16 meters wide at the base. That round shape helped spread weight in every direction, but it could not change the nature of the soil beneath it. The stone still pressed down into clay, sand, silt, shells, and water-rich ground, and the amount of weight was enormous. The tower weighs roughly 14,000 tons. That is the weight of thousands of cars pressing down in one place. Every column, every arch, every stair, every block of marble added to that steady downward force. Even the open arcades, which make the tower look light and airy, are still made from heavy stone. Marble may shine softly in the sun, but it is dense. A single cubic meter of marble can weigh more than 2.5 tons. So the tower's pale surface gives a gentle impression, while its mass tells a much heavier story. The foundation had to carry all of that. Not for one day, not for one season, but year after year, as more levels were added. The problem was not simply that the tower was heavy. Many buildings are heavy. The problem was that the heavy load was being placed on ground that did not press back evenly. A foundation works best when the ground beneath it acts like a steady hand. At Pisa, the hand was softer on one side than the other. As the tower's weight increased, the soil below began to squeeze and settle. If the foundation had reached deeper into firmer material, the tower might have remained straighter. If the base had been wider, the weight might have spread more gently. If the builders had fully understood the buried layers beneath the square, they might have changed the design before the tower rose very high. But medieval builders did not have modern soil tests. They could not drill deep cores and study each layer in a laboratory. They judged the ground by experience, by nearby structures, by what they could see, and by what earlier builders had managed to build in the same area. From the surface, the Piazza dei Miracoli looked calm enough. The cathedral stood nearby. The baptistry was rising too. The grass, paving, and open space gave no clear warning that a tall, narrow bell tower would behave differently from the buildings around it. But height changes everything. A small, uneven movement at the base becomes much larger at the top. A few centimeters of sinking below can shift the upper stones far enough for the human eye to notice. That is why shallow foundations are so risky under tall structures. They do not give the building much room to resist turning. The tower was not yet the famous leaning landmark we know. It was still a construction site. Stonecutters, masons, ropes, pulleys, and wooden scaffolds surrounded the rising circle of marble. But as the first heavy levels pressed into the soft ground, the hidden problem began to show itself. The tower did not need centuries to reveal its weakness. The lean began while the building was still young. The tower's weakness did not wait until it was old. It did not appear after centuries of rain, weather, and slow damage. It began while the tower was still being built. Around the time construction reached the third level, the ground beneath one side had already started to give way. Only a few stories of stone had risen above the lawn. The bell chamber did not exist yet. The upper arcades had not been finished. The tower was still far from the pale, 8-level shape people recognize today. And yet, the tilt had begun. That detail makes the story feel very different. The builders were not watching an ancient structure slowly sag with age. They were watching a new building shift under its own weight. The tower was still surrounded by scaffolding. Wooden beams would have framed the lower levels. Ropes, pulleys, chisels, carts, and stone blocks would have filled the site. Masons were still shaping the marble. Workers were still lifting materials into place. The building was still becoming itself. But underneath, the soil was already responding. Each new ring of stone added more pressure. Each column and arch sent more weight downward through the shallow foundation. And because the ground was softer on one side, the tower did not settle evenly. It began to lean toward the south. At first, the movement may have been slight, a small difference in level. a line that did not look perfectly vertical, a gap between what the builders expected and what the stones were quietly doing. But tall buildings make small errors easier to see. A tiny tilt near the bottom becomes more noticeable with every meter of height. By the time a few levels were complete, the tower was already showing that something below it was not behaving as planned. This is one of the most important parts of the tower's story. The Leaning Tower of Pisa did not become strange after it was finished. It was born into its problem. The lean was not an old scar added later. It became part of the structure, while the structure was still growing. You can picture a stack of heavy stone plates being built upward one layer at a time. If the lower plates begin to sink more on one side, every new plate above them inherits that angle. The workers can keep adding material. They can try to adjust. They can measure, observe, and adapt. But the building is no longer rising from a perfectly level start. It is rising from a mistake already written into the base. In modern construction, this kind of early movement would be a serious warning. Engineers would stop work. They would study the soil. They would measure the settlement, which means how much the ground is sinking under the load. They might redesign the foundation before adding more weight. But in the late 12th century, builders did not have laser levels, soil pressure sensors, or computer models. They had plumb lines, water levels, experience, and the visible behavior of the stone. A plumb line is a simple tool made from a weight hanging on a string. Because gravity pulls the weight straight down, the string shows a true vertical line. If a wall drifts away from that line, the builder can see it. So the lean would not have been completely invisible. Someone on that medieval construction site must have noticed that the tower was no longer rising straight. The problem was clear enough to matter, but not simple enough to solve. The tower had already cost time, labor, money, and pride. Pisa was a powerful maritime city, trading and fighting across the Mediterranean. Its cathedral complex was a statement of wealth and faith. To abandon the tower after only a few levels would have meant admitting that the city's grand bell tower had failed before it could even ring. So the builders faced a quiet choice. They could stop. They could tear it down. Or they could keep going and try to correct the lean as the tower rose. They chose the strangest path. They did not erase the mistake. They built with it. And from that moment on, the tower was no longer just a round marble bell tower on soft ground. It became a structure shaped by correction, compromise, and a long effort to persuade stone to stand where the earth had already begun to move. Once the tower had begun to lean, the builders were no longer working with a clean design. They were working with a living problem in stone. The lower levels had already shifted. The foundation had already settled unevenly. And every new block placed above the lean would add more weight to a structure that was no longer perfectly upright. So the builders tried to correct it as they went. They did not have modern cranes. They did not have steel braces. They did not have digital instruments measuring the tower's movement by fractions of a millimeter. They had eyes, hands, plumb lines, wooden scaffolds, and long experience with stone. A plumb line could show them the true downward pull of gravity. The tower's walls showed them something else. The marble was rising away from that line, Instead of tearing the structure down, later builders made small changes in the upper levels. They built some parts slightly taller on one side than the other. The goal was simple. If the tower was leaning south, then the new masonry could be adjusted to pull the upper structure back toward a straighter line. It was not a perfect fix. It was more like building carefully on top of a crooked beginning. You can picture a stack of plates on a soft table. If the bottom plate tilts, every plate above it wants to follow the same angle. You might try to correct the stack by sliding the next plate a little the other way, then the next one a little more. The stack may look better from a distance. It may even stand. But it is no longer a simple straight column. It has become a record of each correction. The Tower of Pisa carries that same quiet record. Its lean is famous, but its shape is not just a straight line tipped to one side. The tower has a subtle curve. The lower part leans one way. The upper parts show the builder's effort to adjust. Stone by stone, level by level, they tried to guide the tower back. This is why the tower can look almost alive when seen from the right angle. It does not appear like a clean object simply rotated in space. It looks like something that grew under pressure. A white marble body rising from soft ground, bending as people tried to save it. Those corrections likely happened over more than one building phase. The tower was not completed quickly. Its construction stretched across generations, with long pauses between periods of work. Different builders inherited the problem from those before them. They did not begin with a blank site. They began with a tower already leaning, already heavy, already tied to the unstable ground below. Each decision had to respect what was already there. Adding stone too aggressively could make the lean worse. Changing the shape too much could weaken the design. Doing nothing would allow the tower to keep rising in the wrong direction. So the correction became gentle and practical. Not dramatic, not perfect, just enough to keep building. The upper floors were shaped with small differences in height, creating a slight banana-like curve in the tower's vertical line. That curve is easy to miss in a casual photograph. The eye notices the overall lean first. But the curve matters because it shows the tower was not simply abandoned to gravity. It was negotiated with. The builders were trying to answer the ground with geometry. Geometry is the study of shapes, lines, angles, and space. In this case, geometry was not just drawn on parchment. It was built into marble. Every adjusted level became a quiet argument against collapse. The arches still circled the tower. The columns still repeated in graceful rows. The white stone still caught the Tuscan light. But hidden inside that beauty was a long struggle between human intention and the pull of the earth. The builders wanted a bell tower. The soil gave them a tilt. Their answer was to keep building upward, while bending the design back toward balance. And because of that, the tower became more than a mistake. It became a layered memory of correction, a structure where each level tells part of the story. The lower stones remember the first sinking. The upper stones remember the attempt to resist it. And the whole tower stands as a slow, visible record of people trying to fight gravity without fully understanding the ground beneath their feet. The tower's shape was not corrected in one steady burst of work. It rose slowly, then stopped, then rose again, then stopped again. This uneven rhythm may have become one of the reasons it survived. Construction began in 1173, during a powerful period in Pisa's history. At the time, Pisa was a maritime republic, a city-state whose wealth came from ships, trade, and military power across the Mediterranean. Its fleet sailed to places like Sardinia, Sicily, North Africa, and the Eastern Mediterranean. The cathedral complex was not only a religious space, it was also a public statement. White marble, carved arches, bronze doors, and open green lawns all showed that Pisa had money, skill, and confidence. But medieval Italy was not calm for long stretches of time. Cities fought each other often. Pisa struggled with nearby rivals, especially Genoa, Lucca, and Florence. These conflicts pulled money, workers, and attention away from building projects. So the tower did not rise smoothly from foundation to bell chamber. After the first phase of construction, work stopped for many years. By then, the tower had only reached its lower levels, and the lean had already begun. From one point of view, the pause looked like a delay. From another, it may have been a gift. The soil beneath the tower needed time to adjust. When heavy stone presses down on wet clay and loose sediment, the ground does not always finish settling right away. Water trapped between tiny clay particles must slowly squeeze out. The grains and particles shift closer together. The layer becomes thinner and firmer under the load. This process is called consolidation. It simply means that soft ground becomes more compact as pressure stays on it over time. If the builders had rushed upward quickly, adding all 14,000 tons over a short period, the soil might have failed more suddenly. More weight would have pressed into ground that had not yet settled. The lean could have grown faster. The tower might have crossed the line from strange to unsafe before its upper levels were even built. Instead, history slowed the project down. The lower stones sat in place for decades. Rain fell. The water table rose and fell underground. The clay layers squeezed and adjusted. The tower, already leaning, quietly pressed itself deeper into the earth. By the time workers returned, the ground beneath part of the structure may have been more settled than it had been at the start. This did not fix the lean. It did not make the soil strong in the way bedrock is strong, but it may have reduced the chance of sudden movement. Later phases of construction continued into the 13th century. More arcaded levels were added above the tilted base. The builders still had to work with the curve and the lean that had already formed. Then, after more interruptions, the bell chamber was finally completed in the 14th century, around 1372. From the first stones in 1173 to the final upper chamber, nearly 200 years had passed. That is an unusual amount of time for one tower to become complete. Generations changed while it was being built. The first masons never saw the finished top. Children born after the foundation was laid could have lived their whole lives while the tower was still unfinished. The structure became a project passed from hand to hand, from one political age into another. And that long delay gave the tower something a fast project would not have had. Time. Time for the soil to compress. Time for builders to notice the lean. Time for later workers to adjust the upper levels. time for the tower to settle into its strange balance before the full weight arrived. This is what makes Pisa feel so unusual. Its survival was not the result of one perfect plan. It was shaped by mistakes, war, patience, interruption, and slow ground movement. The same conflicts that delayed the builders may have helped keep the tower standing. What looked like a broken schedule may have acted like a hidden safety valve. The tower was not saved by strength alone. It was partly saved by slowness. And as the centuries stretched around it, the leaning marble began to follow a quiet rule of physics. A structure does not fall just because it is tilted. It falls when its weight moves too far beyond the ground that holds it. The tower's long survival comes down to a quiet rule of balance. A leaning object does not fall simply because it leans. It falls when its weight moves beyond the area that supports it. That hidden point is called the center of mass. The center of mass is the place where an object's weight acts as if it were gathered into one point. For a simple, even object, like a straight wooden block, that point is usually near the middle. For a person standing upright, it is somewhere inside the body, around the lower belly. For the Tower of Pisa, the center of mass sits somewhere inside its heavy stone body. The exact position depends on the tower's shape, its walls, its stairs, its upper bell chamber, and the way its marble is arranged. But the idea is simple. Gravity pulls that center of mass downward. If the downward line still lands inside the base, the object can stand. If the line moves outside the base, the object tips over. This is why balance can feel mysterious from the outside, even when the rule is clear. A book can lean on a table and still remain still. A chair can tip back slightly on two legs before it falls. A person can stand with both feet on the floor and lean to one side for a few seconds. The body may feel stretched. The muscles may tighten. The ankle may shift. But as long as the line of weight still falls between the feet, balance can hold. Lean farther, and the body passes a point where the feet can no longer catch the weight. Then gravity does the rest. The Tower of Pisa follows the same rule, only in marble and earth instead of muscle and bone. Its round base is about 15 to 16 meters wide. That base forms the area of support. The tower can lean as long as the invisible line from its center of mass still falls through that support area. The angle matters, but the hidden line matters more. This is why the tower can look more dangerous than it is. The eye sees the lean. The eye sees the upper levels drifting away from the vertical line. The eye compares the tower to the straight cathedral beside it and feels the imbalance immediately. But gravity does not judge by appearance. It follows the path of weight. For centuries, the tower leaned, but not far enough for its weight to escape the base completely. The danger was always there. A leaning structure creates a turning force. A turning force is a push that tries to rotate something around a point. You can feel this if you hold a broom straight upright in your hand. When the broom is vertical, its weight presses down through your hand. But when it leans, the weight starts pulling it around your grip. The farther it leans, the stronger that turning feeling becomes. The Tower of Pisa's lean created that same kind of turning force at its foundation. Every stone wanted to pull the tower a little farther toward the leaning side. the foundation and soil, had to resist that slow rotation. This is why the tower's shallow base and soft ground mattered so much. The problem was not only downward pressure, it was also the sideways effect created by the lean. The tower was pressing into the soil and trying to rotate through it at the same time. Still, for most of its life, the balance point stayed just close enough to safety. That narrow survival gives the tower its strange calm. It was not perfectly secure. It was not simply doomed. It existed between those two states. Standing, but not straight. Stable, but not careless. Heavy, but still held. A stone tower that should have made people nervous, yet continued to ring its bells over Pisa. The physics is gentle to picture. The white marble rises into the sky. The upper floors drift to one side. Inside the stone, an unseen line of weight drops downward through the structure. Below, the foundation waits. As long as that line remains within the base, the tower stands. The tower was never safe because it looked correct. It survived because the unseen balance had not yet crossed the boundary, where gravity would stop waiting. For a long time, the tower's lean was not a charming detail. It was a problem. A stone bell tower was supposed to rise straight. Its bells were meant to hang high above the cathedral, sending sound across Pisa with a steady, trusted presence. In medieval Italy, towers often carried pride. Some were built for churches. Some were built by wealthy families. Some were built by city governments as signs of power. In Bologna, the Asinelli Tower rose to more than 97 meters, far taller than Pisa's bell tower. In San Gimignano, noble families filled the skyline with narrow stone towers, each one showing status and wealth. In Venice, the Campanile of St. Mark became a high landmark for sailors and citizens alike. These towers were admired because they stood tall. They gave people something to look up to. They marked the skyline and made a city visible from a distance. Pisa's tower was different. It became famous because something had gone wrong. Its defect became the thing people remembered. The marble was beautiful. The columns were graceful. The arches were carefully shaped. But millions of people did not come to Pisa only because the tower was round, white, and old. They came because it leaned. That is a strange kind of fame. Most buildings become known for perfection. A dome that seems too wide to stand. A bridge that crosses water with elegant strength. A cathedral window filled with colored glass. The Leaning Tower became known because its failure stayed visible. It is a little like a crack in a piece of pottery becoming the first thing people notice. The cup may still hold water. The glaze may still shine. The shape may still be lovely. But the crack carries the story. It shows that something happened. It turns the object from a smooth design into a memory. The tower's lean did the same thing. It made the building unforgettable. Over time, the defect became an identity. Travelers wrote about it. Artists drew it. Photographers framed it against the sky. Tourists began posing beside it, holding up their hands as if they could push the tower back into place. That simple pose became one of the most repeated travel photographs in the world. A serious structural problem became a playful human ritual. People stood on the grass in the Piazza dei Miracoli, lined up their bodies with the leaning marble, and pretended for a moment that one person could hold back 8 centuries of gravity. The tower became both fragile and familiar. It was no longer just part of the cathedral complex. It became Pisa's symbol. A city that had once been known for ships, trade, war, and religious art, became known around the world for a tower that did not stand straight. That shift changed the meaning of the building. If the tower had been corrected early and made perfectly vertical, it might have become another beautiful medieval campanile. Still important, still historic, still worth visiting, but it would not have carried the same pull on the imagination. The lean gave it a visible mystery. Anyone could understand it without knowing architecture. A child could look at it and feel the question in the body before words arrived. Why has it not fallen? That is the power of the tower's shape. It turns physics into a picture. The viewer does not need formulas to sense imbalance. The tilted white cylinder against the straight sky explains the problem by simply existing. But fame created a delicate new trouble. Once people loved the lean, saving the tower no longer meant making it perfect. A perfectly straight Pisa tower would have felt like a different building. The flaw had become part of its meaning. Engineers and historians would later have to respect that. They could not treat the lean as something to erase completely. They had to treat it as something dangerous, but also precious. The tower needed to be protected from the very defect that made it beloved. And as the bells waited high above the leaning stone, the tower's purpose as a working campanile added more weight to the story. Its identity was not only visual, it was also heavy, musical, and built into the upper chamber, where bronze bells hung near the sky. The tower was never meant to be only a shape against the sky. It was built to make sound. Its purpose was to hold bells for the cathedral complex below. That is why it stands apart from the cathedral, rather than attached to its walls. A freestanding bell tower could lift sound above the roofline, above the open square, and out across the city. In medieval Pisa, bells were part of daily life. They called people to prayer. They marked the hours. They announced holy days. They could signal mourning, celebration, danger, or public gathering. Before wristwatches, phones, and electric clocks, a bell tower helped organize the day for everyone who could hear it. The Leaning Tower's upper chamber holds 7 bells. They are traditionally linked to the notes of the musical scale. Each bell has its own size, tone, and history. The largest is known as l'Assunta. It weighs more than 3.5 tons. That is heavier than many modern cars. The other bells are smaller, but still heavy pieces of bronze, each hanging high inside the open bell chamber. Bronze is an alloy, meaning a mixture of metals. Bell bronze is usually made mostly of copper, with tin added to make it harder and more resonant. Resonant means it can vibrate clearly and hold a ringing tone. When a bell is struck, the metal does not simply make one sound. It vibrates in many patterns at once. The rim, the sides, and the crown of the bell all move slightly, sending waves through the metal and then into the air. Those waves become sound. Inside the tower, each bell was more than a musical object. It was also a weight. And the higher a heavy object sits in a structure, the more important balance becomes. A stone at the base presses almost straight into the ground. A heavy bell near the top does that too. But because it sits high above the foundation, its weight matters more when the tower leans. You can picture holding a long broom upright. If the heavy end is near your hand, it is easier to control. If the heavy end is far above your hand, even a small lean feels stronger. The distance gives the weight more turning power. The tower works in a similar way. The bells did not create the lean. The ground and shallow foundation had already done that. But the bells added mass near the top of a structure already tilted away from vertical. They made the tower's balance more delicate. They also added the issue of motion. A still bell is heavy. A moving bell is heavy in a more complicated way. When a bell swings or is struck, it creates vibration. Vibration is repeated motion, moving back and forth through the bell, the frame, the stone, and the air. In a strong, straight tower on firm ground, those vibrations can be expected and managed. In a leaning tower resting on soft soil, every movement matters more. The sound may be beautiful, but the physics remains present. Bronze rings. Stone carries the tremor. The foundation receives the tiny changes in force. The soil below answers in its slow way. The bell chamber itself was completed in the 14th century, after the tower had already spent generations leaning and settling. By then, the builders were placing the final purpose of the structure at the very top. The tower had become a white marble body shaped by correction and delay. Then the bells gave it a voice. From the lawn below, it is easy to think of the Leaning Tower as a silent monument, a place for photographs, a strange object to look at. But for much of its life, it belonged to sound. The open arches near the top were not only decorative, they allowed the bells to ring outward. Their tones could pass through the air above Pisa, over stone roofs and narrow streets, across the cathedral square, and into the ordinary movement of the city. That makes the tower's story even more delicate. It was not only leaning, it was working. It was carrying weight. It was holding moving bronze in the sky. And as the centuries passed, the marble, the bells, the soil, and gravity remained tied together in one slow system. The tower did not simply sit there. It kept responding to every load placed upon it. And over time, the lean continued to grow. The tower's voice came from the bells, but its slowest movement came from the ground. After the bell chamber was finished in the 14th century, the tower did not become still. It only became complete. The marble had reached its final height. The bells had been placed near the top. The arches and columns had taken their familiar shape. But below all of that, the soil kept answering the weight. The lean continued to grow slowly over the centuries, not like a wall cracking open in a single storm, not like a tree falling in a strong wind, more like a tree bending toward light year after year, except the tower was not reaching for the sun. It was being pulled by gravity and shaped by pressure in the ground. The difference is important. A tree bends because living cells grow more on one side than the other. The Tower of Pisa leaned because dead stone pressed into soft soil, and the soil did not press back evenly. The movement was measured in small amounts, a little more settling under one part of the foundation, a slight increase in the angle, a tiny shift at the top. Day by day, no one walking through Pisa would have seen the tower move. A person could pass it in the morning, return in the evening, and see the same pale marble standing over the grass. But over generations, tiny changes become visible. A child could grow old while the tower's lean increased by only a small amount. Then that person's grandchildren could inherit a tower leaning a little farther than before. That is how slow danger can hide inside familiar beauty. When something changes too gently, people adjust to it. They stop seeing it as movement. They begin to see it as character. The tower became part of Pisa's daily landscape. Markets opened. Church services began. Visitors arrived. Students and travelers crossed the square. Rain darkened the marble in winter. Summer sun brightened it again. And through all of that, the tower kept leaning. The force behind that movement was simple but patient. The tower weighed roughly 14,000 tons. That weight pressed down through a shallow foundation only about 3 meters deep. Because one side of the ground was more compressible, the tower settled unevenly. As the tilt increased, the weight no longer acted straight down through the center of the base. It began to create more turning force. That turning force encouraged the tower to lean farther. The farther it leaned, the more carefully the balance depended on the foundation and soil. This is why the tower's story is not just about one mistake made in 1173. It is about a mistake that stayed active. The original choice of ground continued to matter for hundreds of years. The soil was not a dead background. It was part of the structure. It held water. It compressed. It shifted with pressure. It carried the tower in a way that was never completely even. By the 20th century, the lean had become too serious to treat as only a charming oddity. The top of the tower had moved several meters away from where it would have been if the tower stood straight. Its angle reached more than 5 degrees before the great modern rescue work began. That may not sound like much. 5 degrees is a small angle on paper. But on a 56-meter tower, a small angle becomes a large sideways displacement near the top. The marble no longer simply rose above the base. It reached outward into the air. Yet because the growth of the lean was so slow, Pisa lived beside it for centuries. People had time to become used to the impossible-looking shape. The danger did not shout. It whispered through measurements, cracks, soil pressure, and the slow path of the tower's weight. That may be the quietest part of the mystery. A structure can move for hundreds of years without seeming alive. A city can grow around a problem until the problem feels like a symbol. And for a long time, the same soft earth that made the tower lean may also have helped it survive forces that could have brought down a straighter, stiffer building. The tower had been leaning for centuries, yet it had also been surviving. That survival is stranger when the ground begins to shake. Italy is one of the more earthquake-prone countries in Europe. The long Apennine Mountains run down the Italian peninsula like a spine, and the region is shaped by the slow movement of Earth's crust. Large pieces of crust, called tectonic plates, press and shift over time. Those movements can store stress in rock until the stress releases as an earthquake. Pisa is not in the most violent earthquake zone in Italy, but over more than 800 years, the tower has still lived through several strong tremors in the wider region. A tall, leaning marble tower on soft ground sounds like exactly the kind of structure that should have suffered badly. And yet, it did not collapse. The same soil that caused the lean may also have helped protect it. This is one of the most surprising parts of the tower's story. The ground beneath Pisa was weak under steady weight. It compressed slowly under the tower's 14,000 tons. It allowed one side of the foundation to sink more than the other. That weakness gave the world the famous lean. But during shaking, soft ground can behave in a different way. It can act less like a hard stone floor and more like a cushion. A cushion may not be good at keeping a heavy object perfectly level for hundreds of years. Over time, the object may sink into it. One side may settle more than the other, but if a sudden jolt passes through, the cushion can soften some of that sharp motion. It can stretch the shaking out. It can change the rhythm of the vibration before it reaches the object above. Engineers call this soil structure interaction. The phrase sounds technical, but the idea is simple. A building and the ground beneath it do not move separately during an earthquake. They move together. The soil shakes the building. The building pushes back into the soil. The two become one connected system. This matters because every structure has a natural rhythm. If you gently push a swing at the right moment, it moves higher. That is because your pushes match the swing's rhythm. Buildings can behave in a similar way during earthquakes. If the shaking of the ground matches the natural rhythm of the building, the motion can grow stronger. That matching effect is called resonance. Resonance can be dangerous because it lets small, repeated motions build into larger ones. At Pisa, the tower and its soft soil created an unusual rhythm together. The tower is tall, heavy, and stiff. The soil beneath it is soft and layered. Instead of forcing the tower into the most damaging kind of vibration, the soil appears to have changed the way earthquake energy moved through the structure. The ground that failed under slow pressure may have reduced the effect of sudden shaking. So the tower's weakness was not simple. It was not only harmful. It was not only protective. It was both. Under the slow, constant pull of gravity, the soft soil allowed the tower to lean. Under the brief, violent motion of earthquakes, that same softness may have helped keep the tower from shaking apart. The image is almost peaceful. The white marble rises above the lawn. The foundation rests in clay, sand, shells, and water-rich sediment. A tremor passes through the ground. The soil moves. The tower answers. But instead of a sharp, brittle fight between stone and earth, the motion becomes slower and more forgiving. This does not mean the tower was safe. It means its danger was delicate. The ground beneath Pisa was not simply an enemy. It was part of the tower's survival. That made the problem much harder for the people who later tried to save it. They could not treat the soil as something to replace without consequence. They could not treat the lean as something to erase quickly. The very weakness that threatened the tower had also been woven into the strange balance that kept it standing. To touch the tower carelessly was to disturb that balance. To change the ground too much was to change the quiet system that had protected it for centuries. By modern times, the tower had become more than an old building with a famous tilt. It had become a delicate system. The marble, the bells, the foundation, and the soil were all connected. Change one part too quickly, and another part could answer in a dangerous way. This is why saving the tower was never as simple as pushing it straight. A person looking at the tower from the lawn might imagine a simple repair. Pull the top back, strengthen the base, add support on the leaning side, make the tower upright again. But old structures do not respond like drawings on paper. They respond through weight, cracks, pressure, moisture, and hidden contact with the ground. By the 20th century, engineers understood that the tower's survival depended on a narrow balance. Its center of mass still fell close enough through the foundation to keep it standing. But the margin was small. If workers shifted the tower too quickly, the line of weight could move in a harmful direction. If they changed the foundation unevenly, the soil could settle in a new and unexpected way. If they made the tower too stiff in one place, stress could gather somewhere else. Stress, in engineering, simply means force inside a material. Stone can carry great pressure when it is compressed straight down. But stone is weaker when it is pulled, twisted, or bent. The Tower of Pisa was made from masonry, which means stone units joined together, rather than one solid carved piece. Masonry can last for centuries, but it does not like sudden changes. It prefers steady loads. It prefers compression. It does not forgive careless movement. That made every possible repair feel risky. Straightening the tower too aggressively could have shifted the loads through the walls and foundation. A load is just the weight or force a structure must carry. For centuries, the tower's stones had settled into one strange pattern. The lower levels had compressed. The upper levels had been adjusted. The foundation had pressed into the soil in its own uneven shape. Even the lean had become part of how the tower carried itself. To force it quickly toward vertical could have disturbed that pattern. It would be like taking an old, warped wooden door and trying to make it perfectly flat in one motion. The wood might not gently obey. It might split. The tower was far heavier and far less forgiving. Engineers also had to think about the soil. The ground beneath the tower was not a simple block. It was layered with clay, sand, shells, silt, and water. Some layers drained slowly. Some compressed more than others. Some reacted differently when pressure changed. If too much weight was added to one side, the soil might sink more. If too much material was removed, the foundation might shift too far. If water moved through the ground in a new way, the buried layers could soften. This is why the safest repair had to be slow, not dramatic, not forceful, not a single bold act. The goal was to change the tower without waking the hidden instability beneath it. That meant listening to the structure through measurement. Engineers studied the angle of the lean. They studied cracks in the masonry. They studied the foundation. They studied how the soil responded when forces changed. Modern instruments could detect tiny movements that medieval builders could never have measured. A few millimeters mattered. A fraction of a degree mattered. A slow shift over weeks could tell engineers whether the tower was relaxing into safety or moving toward danger. The tower had become a puzzle where every solution carried a possible cost. Leave it alone, and the lean could keep growing. Pull it too hard, and the structure could be damaged. Dig in the wrong place, and the ground could answer badly. Add support carelessly, and the tower might depend on that support forever. Saving Pisa meant accepting that the tower was not a normal building anymore. It was a balance built from mistakes, delays, corrections, and soft earth. The challenge was not to defeat the lean, it was to guide it. And before modern engineers found the careful path, earlier attempts to help the tower showed just how easily a rescue could become part of the problem. The danger of the tower was not only that it leaned. The danger was that people kept trying to help it. And with Pisa, even help could become risky. When a structure rests on soft, wet, layered ground, the soil beneath it is not just empty space. It is part of the building's behavior. Clay, sand, silt, shells, and groundwater all share the weight in different ways. If someone changes that ground, the pressure can shift. If someone digs too close to the foundation, water can move. If someone adds material in the wrong place, one side may become heavier than before. Even a repair made with good intentions can quietly change the balance. One of the clearest examples came in 1838. An architect named Alessandro della Gherardesca began work around the base of the tower. At the time, part of the lower base had become buried by centuries of rising ground level. The goal was to reveal the original foundation and create a walkway around it. From the surface, this may have seemed reasonable. The lower marble could be seen again. The monument would look more complete. Visitors could walk around the base and admire the old stonework. But the excavation disturbed the ground near the foundation. When workers dug around the base, water entered the area. The soil conditions changed. The tower's lean increased. A project meant to improve the monument had made the hidden problem worse. It is a little like pushing on one side of a stuck object and accidentally loosening the wrong side. The object moves, but not in the way you wanted. With a small object, you can catch it. With a 14,000-ton tower, every mistake becomes slower, larger, and harder to reverse. Another famous attempt came during the 20th century, under Benito Mussolini. Mussolini disliked the idea that one of Italy's most famous monuments leaned. He wanted the tower to stand straighter, as if a perfect vertical line would better represent national strength. In the 1930s, workers drilled hundreds of holes into the foundation and injected cement grout beneath the tower. Grout is a liquid mixture, often made with cement, that hardens after being pumped into spaces. The idea was to strengthen the base. But the tower did not become safely upright. The added material changed the ground and the foundation behavior in ways that were not fully controlled. The lean worsened. Again, the tower showed that it could not be treated like an ordinary repair job. The problem was not just weak stone. The problem was the whole system. A leaning masonry tower, a shallow foundation, soft ground, groundwater, uneven pressure, and centuries of slow settlement already locked into place. When people tried to force a simple solution onto that system, the tower answered in its own way. This is why Pisa became such a difficult engineering lesson. Adding strength is not always the same as adding safety. a structure can be made heavier in the wrong place. A foundation can be stiffened unevenly. Water-rich soil can respond badly when it is dug, drained, pumped, or pressed. The ground under the tower was not a solid table waiting to be repaired. It was a layered, damp, slowly moving support system that had been carrying the tower for centuries. Each intervention changed the way weight traveled from the marble into the earth. That path of weight mattered more than appearances. A repair could look sensible above ground and still fail underground. By the late 20th century, engineers had inherited not just the original medieval problem, but the long history of attempts to correct it. The tower had survived its shallow foundation. It had survived centuries of increasing lean. It had survived earthquakes. It had survived repairs that made its condition worse. But survival was not the same as safety. The angle had grown too large. The top had drifted too far from where it would have stood if the tower were straight. The old charm of the lean was beginning to look less like a curiosity and more like a warning written slowly in marble. Pisa's tower had become a beloved landmark, but it was nearing a point where beauty alone could no longer protect it. By the late 20th century, the tower's slow lean could no longer be treated as only a beautiful oddity. For hundreds of years, it had stood in the open square. Visitors had climbed its spiral stairs. Bells had hung in the upper chamber. The marble had weathered rain, sun, wind, and the slow passing of generations. But the angle kept growing. By 1990, the tower was leaning by about 5.5 degrees. On paper, that number can seem small. 5.5 degrees is not even the angle of a steep roof. It is less than the angle of many ramps and hills. But on a tower more than 50 meters tall, that small angle becomes serious. The top of the tower was leaning several meters away from where it would have been if the tower stood straight. The marble cylinder no longer simply rose from its base. It reached outward. Gravity was no longer just pressing down through the tower. It was also pulling the tower around its foundation, trying to increase the tilt. That is why the closure in 1990 mattered so much. On January the 7th of that year, the tower was closed to the public. For visitors, it meant the famous climb was over for a time. No more footsteps winding up the narrow inner staircase. No more looking out through the open arches near the top. No more standing inside the leaning stone body and feeling the strange angle beneath your feet. For engineers, the closure meant something deeper. The tower had crossed from preservation into emergency engineering. Preservation usually means caring for something old, cleaning stone, repairing cracks, protecting art from weather, replacing damaged pieces with great care. But emergency engineering means the structure itself is in danger. The question is no longer only how to keep the building beautiful. It is how to keep it standing. The fear was not imagined. In March of 1989, another medieval tower in Italy had collapsed. The Civic Tower of Pavia, built of brick and stone, suddenly fell after standing for centuries. Its collapse killed 4 people and shocked the country. It reminded engineers, officials, and the public that old towers can look familiar right up until the moment they fail. A famous monument is still a physical object, Stone has limits. Foundations have limits. Soil has limits. Pisa's tower had not collapsed, but its long survival could not be used as proof that it would survive forever. That is one of the quiet lessons of old structures. The fact that something has stood for 800 years does not mean it is safe for 800 more. It only means the balance has held so far. At Pisa, the balance had become too narrow to ignore. The tower weighed roughly 14,000 tons. Its foundation was only about 3 meters deep. The ground beneath it remained soft, layered, and water-rich. Its center of mass still fell close enough through the base for the tower to stand. But the margin had grown smaller as the lean increased. Engineers had to think about the tower almost like a slow-moving patient. They had to measure its angle. They had to study the soil. They had to understand old cracks and newer movements. They had to know how much the tower could shift before the risk became unacceptable. And most importantly, they had to act without making the problem worse. That was the difficulty. The tower was not a fallen building waiting to be rebuilt. It was a standing building that had to be gently guided away from collapse. Too much force could damage the masonry. Too much digging could disturb the soil. Too much straightening could erase the very shape the world had come to love. The closure in 1990 turned the Leaning Tower of Pisa from a tourist wonder into one of the most delicate engineering projects in the world. After more than 8 centuries of slow survival, science finally had to step in. But the goal was not to defeat the lean completely. The goal was to save the tower while leaving its strange, beloved imperfections still visible against the sky. The rescue of the tower had to begin with a strange kind of restraint. Engineers were not trying to make the Tower of Pisa perfectly straight. That may seem surprising at first. After all, the lean was the problem. It had pulled the tower toward danger for centuries. It had closed the tower to visitors in 1990. It had turned a beautiful medieval bell tower into a structure that needed urgent care. But by then, the lean was also the tower's identity. A straight Tower of Pisa would still have been old. It would still have been made of pale marble. It would still have stood beside the cathedral and baptistry in the Piazza dei Miracoli. But it would no longer be the building the world recognized. The goal was not to erase the mistake. The goal was to make the mistake safe enough to survive. That required a very careful target. The tower needed to be pulled back from the edge, but not returned to perfect vertical. Vertical means straight up and down, following the direction of gravity. For most towers, vertical is the ideal. For Pisa, perfect vertical would have felt like a loss. The lean had become part of the monument's history, part of its beauty, and part of the reason people cared about saving it. So the engineers had to protect both the structure and the story. They had to reduce the tilt enough to move the center of mass into a safer position. But they also had to leave enough tilt for the tower to remain itself. It was like helping someone regain balance without forcing them into a stiff, unnatural pose. A person who has nearly slipped does not need to stand like a statue. They only need their weight brought safely back over their feet. The tower needed the same kind of help. Not a complete correction, a controlled return towards safer balance. That idea shaped every part of the rescue. The tower weighed about 14,000 tons. It stood more than 50 meters high. Its foundation reached only about 3 meters down into soft layered soil. Its walls were made from old masonry, meaning stone joined together in courses rather than one single solid piece. Every part of it had settled into its tilted position over hundreds of years. If engineers tried to force the top backward too quickly, the stone could crack. If they braced it too strongly in the wrong place, new stresses could appear inside the walls. If they disturbed the foundation carelessly, the ground could shift again. The safest answer would have to be slow enough for the tower to respond gently. It would also have to be subtle. The face of the tower, with its arches and columns, could not simply be covered in permanent steel. The monument had to remain open, readable, and beautiful. The solution had to work mostly where the original problem began, beneath the tower, inside the ground. That was the quiet wisdom of the modern rescue. The tower had leaned because the soil settled unevenly, so the tower would have to be stabilized by changing how the soil supported it. Not by yanking the marble back into place, not by pretending the tower was a modern steel frame, but by guiding the foundation slowly, using the same patient forces that had shaped the lean in the first place. The rescue team had to think in millimeters. A millimeter is about the thickness of a small coin. Movements that tiny could matter because the tower was so tall. A small shift at the foundation could become a visible change near the top. The process had to be measured constantly, like watching the breathing of an old stone body. Each adjustment needed time. Each movement had to be checked before the next one. This was not a battle against the tower. It was a negotiation with it. The tower had survived through softness, delay, and balance. The rescue had to use those same qualities: quiet changes, slow movement, careful measurement, respect for the lean, but not surrender to it. The marble could stay almost exactly as visitors remembered it. The open arches could still catch the Tuscan light. The tower could still lean against the sky. But beneath the grass and stone paving, the real work would begin, in the soil that had first pulled the tower away from straightness. The real rescue began where the original trouble had begun. Not at the top of the tower, not in the bell chamber, not in the marble arches that visitors could see from the lawn. It began beneath the foundation, in the soft ground that had been carrying the tower since 1173. The main method was called soil extraction. It is also often called under-excavation. The idea sounds almost too simple. Instead of pushing the leaning side upward or pulling the top backward, engineers removed small amounts of soil from beneath the higher side of the foundation. The tower leaned toward the south, so the north side was the higher side. By carefully removing soil from under that higher northern side, engineers allowed that side to settle downward a little. As the north side settled, the tower rotated very slowly back toward the north. The lean became smaller, not gone, just safer. This was a gentle way to work with gravity instead of fighting against it. Gravity had helped create the problem by pulling the tower's weight into soft ground. Now gravity could help solve part of the problem too. The engineers did not need to grab the tower and force it upright like a pole. They changed the support beneath it, then let the tower's own weight guide the movement. You can picture a heavy table standing unevenly on a thick rug. If one leg sits too high, you could try to shove the whole table sideways, but that might twist the legs or spill everything on top. A calmer method would be to adjust the rug under the high leg, little by little, until the table settles into a better position. Pisa's tower was far more delicate, but the principle had that same quiet patience. The soil was not removed in great chunks. It was removed slowly through carefully placed holes. Engineers used angled drilling beneath the foundation, taking out small amounts of earth in a controlled pattern. Each small removal changed the pressure underground. Each change allowed the foundation to settle by a tiny amount. And after each movement, the engineers waited and measured. They watched the tower's angle. They watched the ground. They watched the stone. They had to know whether the tower was moving safely or whether the soil was responding too quickly. That waiting was part of the method. The tower had leaned slowly over centuries, so the rescue could not be rushed in days. Even a few millimeters mattered. A small movement at the base could become a much larger change at the top, because the tower rose more than 50 meters into the air. When the foundation shifted, the upper marble answered. The whole tower moved as one connected body. This is why soil extraction was so elegant. It respected the tower's age. It respected the soil's softness. It did not pretend that the tower could be treated like modern steel. Masonry does not like sudden force. Old stone, mortar, arches, and columns need time to adjust. By working through the ground, engineers avoided placing harsh stress directly on the visible structure. The method also respected the tower's identity. A full straightening would have erased the familiar lean, but a slight reduction could move the center of mass into a safer position while leaving the tower visibly tilted. The goal was not perfection. The goal was survival. Over time, the tower began to settle backward in the intended direction. The movement was slow enough to seem almost invisible. No dramatic moment marked the correction. There was no single pull, no sudden lift, no loud turning point. Just earth removed in small amounts. Measurements checked again and again. Gravity doing quiet work beneath marble. The tower's rescue became the opposite of its fame. The fame was visual, obvious, and instantly recognizable. The rescue was hidden, patient, and precise. Above ground, the tower still leaned in the Tuscan light. Below ground, the foundation was being persuaded into a safer balance. And because even gentle persuasion needed protection, engineers surrounded the process with counterweights, cables, and constant watching, making sure the tower never moved faster than it could safely bear. Because the tower was being persuaded through the ground, every part of the rescue needed a safety net. The engineers could not simply remove soil and hope the marble answered gently. They had to control the movement from several directions at once. Before the deepest work could continue, temporary lead counterweights were placed on the north side of the tower. That was the higher side. It was the side opposite the lean. Lead was useful because it is extremely dense. A small block of lead weighs far more than the same size block of stone or wood. By stacking hundreds of tons of lead ingots on the north side, engineers could add stabilizing weight without building a huge visible structure around the tower. The weights pressed down where the tower needed help staying controlled. They did not fix the lean by themselves. They acted more like a careful hand placed on the safer side of the structure, while the real correction happened below. You can picture someone steadying a heavy ladder, while another person adjusts its feet. The hand does not carry the whole ladder. It reduces the chance of a sudden slip. At Pisa, the counterweights helped reduce risk, while engineers prepared the tower for slower, more exact work. Support cables were also used as a backup. These were not meant to yank the tower upright. They were there to restrain dangerous motion if the tower began moving too far or too fast. The tower's marble body had stood for centuries, but during restoration, it was briefly more vulnerable because the soil beneath it was being changed on purpose. So the cables acted like quiet guardians. They helped make sure a controlled correction did not become an uncontrolled movement. Around the tower, modern monitoring instruments watched changes too small for the eye to see. Engineers measured the angle of the tower. They measured tiny shifts in the stone. They measured movements in the foundation and soil. They used instruments that could detect changes of only a few millimeters. A millimeter is smaller than the thickness of many grains of rice. On a table, a millimeter might seem meaningless. On a tower more than 50 meters tall, it could signal the beginning of something important. The rescue was not based on one measurement. It was based on repeated measurement over long periods. The tower moved. Then engineers waited. The soil settled. Then they checked again. A little more soil could be removed. Then more waiting. Then more measuring. This patience was not just caution. It was part of the science. Soft ground does not always respond instantly. Clay, especially when it holds water, can keep changing after pressure shifts. Water moves slowly through tiny spaces between clay particles. The soil may continue to settle after the first change is made. If engineers had rushed, they might have mistaken a temporary pause for true stability. So the rescue had to follow the pace of the earth itself. Slow pressure, slow response, slow correction. The tower became a structure watched almost like a living patient. Its lean was checked. Its small movements were recorded. Its foundation was studied. Its response guided the work. Every number told part of the story. If the tower moved in the desired direction, the method could continue. If the movement became too large or too quick, the work could be slowed or stopped. This is what made the rescue so different from earlier attempts. The tower was not being forced into a theory. The tower was being listened to. The lead weights, the cables, and the instruments all served that purpose. They allowed engineers to make tiny changes while keeping the old marble safe. Above the square, visitors could still recognize the tilted shape. Below and around it, the rescue was unfolding through weight, tension, and measurement. The work was quiet, but the stakes were immense. Every small movement mattered because the engineers were guiding an 800-year imbalance away from collapse. And little by little, the tower began to come back from the edge. Little by little, the tower answered. The change was not dramatic from the outside. There was no sudden straightening. No moment when the tower visibly swung back into place. The rescue worked in the quiet language of small movements. Soil was removed. The foundation settled. The instruments recorded the response. Then the engineers waited again. Over time, the top of the tower moved back by roughly 40 centimeters. That is a little less than half a meter. It is about the length of a school ruler, plus a little more. For a person standing beside the tower, 40 centimeters at the top might not sound like much. The tower still leaned. It still looked like Pisa. It still held the same strange shape against the sky. But for the physics of the structure, that small movement mattered deeply. The top of a tall tower acts like the end of a long lever. A small change in angle can shift the line of weight enough to reduce the turning force at the base. The tower did not need to become vertical. It needed to move away from the edge of failure. That is what the restoration achieved. The lean was reduced from its most dangerous modern angle, and the tower's center of mass moved into a safer position above the foundation. The work took more than a decade. The tower had closed to visitors in 1990. It reopened in 2001. For 11 years, the famous climb was paused while engineers, geologists, architects, and conservation experts worked through the problem with unusual patience. Geologists study earth materials like rock, soil, and sediment. Conservation experts protect old buildings and artworks without damaging their historical value. At Pisa, both kinds of knowledge were needed. This was not only a soil problem, it was also a monument. The rescue had to protect the tower's structure, its appearance, and its long history. When visitors were finally allowed back inside, they could climb the spiral staircase again. There are nearly 300 steps inside the tower. The stairs curve upward through the thick stone walls, and they have been worn by centuries of feet. Some steps are slightly hollowed in the middle from use. As people climb, the lean can be felt in the body. The floor seems to shift. The walls do not feel quite like the walls of an ordinary tower. The experience reminds visitors that the building was saved, not made normal. That distinction matters. The tower was not transformed into a straight modern structure. It was not rebuilt from the ground up. It was not corrected into perfection. It remained a leaning medieval bell tower made of old stone, resting on old soil, carrying the marks of every century it had survived. Engineers estimated that the stabilization had made the tower safe for at least another couple of centuries. That does not mean the tower became permanent in an absolute sense. No building is permanent in that way. Stone weathers, soil shifts. Rainwater moves through the ground. Temperature changes make materials expand and contract. But the rescue gave the tower time. More time to stand. More time to be studied. More time to remain the strange and beautiful object people recognize from all over the world. There is something gentle in the scale of the success. After more than 800 years of leaning, the tower was saved by less than half a meter of correction. Not by erasing its floor, not by hiding it behind supports, not by pretending the medieval mistake never happened. The rescue worked because it understood the tower as it truly was. A heavy stone structure, a shallow foundation, a soft bed of clay, sand, shells, and water-shaped ground. A famous lean that had to be reduced, but not removed. The tower came back from the edge, but it did not leave the edge behind completely. It still stands in balance with the same earth that once betrayed it. The danger was reduced. The story continued. And even after the reopening, the tower remains something that had to be watched, because stone and soil do not stop speaking to each other just because people have finished the repair. The tower was reopened, but it was not forgotten by science. Its rescue did not end the conversation between stone and soil. It only made that conversation safer. Even today, the Leaning Tower of Pisa is monitored because the same forces that shaped it are still present. Gravity still pulls every block of marble downward. The foundation still rests on layered ground. Moisture still moves through the soil. Rain still falls on the Piazza dei Miracoli. Heat and cold still pass through the stone across the seasons. A monument can look still from a distance, but no old building is truly frozen. Stone expands slightly when it warms. It contracts slightly when it cools. Rainwater can enter tiny cracks. Wind can carry dust and salt. Groundwater can rise and fall below the surface. Visitors add small, repeated loads as they climb the inner staircase, step by step, year after year. Each effect may be tiny on its own, but the Tower of Pisa has always been shaped by tiny effects, adding up over long periods. That is why monitoring matters. The tower does not need to move quickly to matter. It only needs to move slowly in the wrong direction. Engineers can watch its angle with instruments far more precise than the plumb lines used by medieval builders. They can measure whether the lean changes by fractions of a millimeter. They can study how the foundation responds after heavy rain or long dry periods. They can compare today's measurements with records from previous years. In this way, the tower becomes almost like a slow clock. Not a clock with hands moving around a face. A clock made of marble, soil, water, and gravity. Each tiny shift is like a quiet tick. Most ticks mean nothing dangerous. They are simply part of the tower being an old structure in a real environment. But if the pattern changes, if the movement begins to grow, or if the soil starts behaving differently, the instruments can notice before the eye can. That early warning is part of what keeps the tower safe. The rescue reduced the lean by roughly 40 centimeters at the top. It gave the monument a safer balance. But it did not change the basic nature of the place. The tower is still a heavy masonry structure. Masonry means stone or brick pieces joined together with mortar. It is strong under steady compression when weight presses downward. But it is less forgiving if it is twisted, pulled, or bent too much. The foundation is still shallow compared with the tower's height. The soil below is still alluvial ground, built by water over long stretches of time. And the tower still leans. That lean is no longer growing in the same dangerous way it once was, but it remains part of the structure. It is still the reason the tower must be understood carefully. An ordinary straight building on solid rock might have a wide margin for small changes. The Tower of Pisa has less room for carelessness. Its history has always lived near the edge of balance. That does not make it fragile in a dramatic way. It makes it sensitive. A sensitive structure needs attention. It needs records. It needs people who understand that preservation is not one finished act. It is an ongoing relationship. The tower's marble may seem permanent in photographs, bright against the blue Tuscan sky. But the building is still responding to the world around it. A wet winter can change the ground. A dry summer can change the moisture in the soil. Small vibrations can pass through the stone. Temperature can open and close tiny cracks too small for visitors to notice. The tower keeps standing because these changes are watched, measured, and understood. That is the deeper meaning of its rescue. Modern engineering did not defeat time. It gave people a way to listen more closely. The tower still belongs to the same forces that nearly destroyed it. Soft soil, shallow foundation, heavy stone, slow gravity. Those forces have not vanished. They have only been brought back into a safer balance. And because that balance continues, the story of Pisa is not finished. The tower remains a living partnership between a medieval dream above the grass and the patient, shifting earth beneath it. The Leaning Tower of Pisa is often remembered as a strange shape. A white marble tower tilted against the sky. A landmark that seems to lean farther than it should. But by now, its deeper lesson is quieter and larger than that. The tower shows that architecture is never separate from geology. Geology is the study of earth materials, such as rock, soil, clay, sand, water, and the slow forces that shape them. A building may be designed by human hands. It may be carved, measured, decorated, and planned. But once it touches the ground, it becomes part of the Earth's own system. The tower's marble came from quarries. Its columns were shaped by masons. Its bells were cast in bronze. Its stairway was worn by human feet. Yet its fate was decided just as much by clay, silt, shells, river sediment, and groundwater. That is the quiet truth beneath Pisa. A building can be made of strong stone and still depend on weak soil. The tower's white marble looks solid. Its arches repeat with calm order. Its round walls have lasted through wars, weather, and centuries of visitors. But the tower never stood alone. It always stood on something. And that something was not a simple block of rock. It was soft alluvial ground, laid down by water over long spans of time. The same idea appears in many famous places. Venice, for example, was built on islands in a lagoon, where soft mud and water shaped every choice. Many Venetian buildings rest on wooden piles driven into wet ground. A pile is a long post pushed deep into soil to support weight. Those piles survive because they were sealed away from air underwater, slowing the decay that would normally destroy wood. The beauty above the canals depends on hidden supports below them. Mexico City tells another version of the same story. Much of the city was built on the old lakebed of Lake Texcoco. Soft clay beneath the city has compressed as water has been pumped from underground. As a result, some buildings have sunk unevenly over time, including parts of the Metropolitan Cathedral, whose construction began in the 16th century. The stone is strong. The history is grand. But the lakebed below still matters. Machu Picchu, high in the Andes of Peru, shows the opposite kind of wisdom. The Inca builders placed the city on steep mountain terrain, where heavy rain could have destroyed walls and terraces. Instead of ignoring water, they designed for it. They built drains, stone channels, terraces, and carefully layered foundations that carried rain away. At Machu Picchu, survival depended not only on stone cutting, but on understanding how water moves through a mountain. The Roman Colosseum carries another lesson. Its arches and concrete helped it stand for nearly 2,000 years. But earthquakes, stone removal, fire, and ground movement changed its shape. The missing outer wall on one side is part of that long physical history. Even a monument built with great skill keeps answering the forces around it. Pisa belongs in this wider family of structures. It reminds us that a landmark is not only what rises above ground, it is also what happens below. Drainage can decide whether walls stay dry. Foundations can decide whether weight spreads safely. Earthquakes can reveal weaknesses that daily life hides. Groundwater can soften soil or shift pressure beneath a building. A structure may look still, but it is always negotiating. Stone negotiates with rain. Foundations negotiate with soil. Walls negotiate with gravity. The tower in Pisa makes that negotiation visible because it leans. Other buildings hide their struggle more quietly. Their foundations sink by millimeters. Their stones crack along old joints. Their floors settle gently over centuries. Pisa simply shows the conversation in a way anyone can see. The tower is no longer only a curiosity. It is a reminder that human dreams always meet the earth somewhere. A cathedral, a palace, a bridge, a tower, or a city can rise from plans and measurements, but it survives through clay, water, rock, weather, and time. The Leaning Tower stands because people learn to respect that hidden partnership. Its beauty is above the grass. Its lesson is beneath it. And the longer it stands, the more clearly it shows that even our strongest monuments are never separate from the ground holding them. The tower's lesson has always been hidden in plain sight. It looks like a building caught in failure, but it is also a building that survived its own mistake. The chain began with the ground. Pisa sits on a low plain shaped by the Arno River, water, marshland, and old coastal sediments. Beneath the tower were layers of clay, sand, silt, shells, and groundwater. This was alluvial soil, meaning loose material laid down by moving water over long periods. It could hold weight, but not always evenly. Then came the foundation. For a marble tower that would rise more than 50 meters high and weigh roughly 14,000 tons, the base reached only about 3 meters into the ground. That shallow foundation gave the tower little anchoring depth. The stone pressed downward. The softer layers below squeezed and settled. One side gave way more than the other, and the tower began to lean while it was still young. Construction started in 1173. By the time the builders had reached only the lower levels, likely around the 3rd story, the tilt had already appeared. This means the tower was not an old structure slowly wearing out. It was a new structure already reacting to the earth beneath it. The builders saw the problem and chose not to abandon it. They adjusted. They made later levels slightly taller on one side. They tried to guide the upper parts back toward balance. That is why the tower does not lean as one perfectly straight tilted column. It carries a subtle curve, like stone remembering each attempt to correct it. Then history added its own strange help. Construction did not continue smoothly. Wars, political conflict, and Pisa's struggles with rival cities interrupted the work. The full process stretched from 1173 into the 14th century, with the bell chamber completed around 1372. Those long pauses may have helped the tower survive. The soil had time to compress slowly. Water could move through the clay. The ground could settle before more weight was added. What looked like delay may have acted like protection. The tower survived because its center of mass stayed just close enough above its base. The center of mass is the hidden point where an object's weight acts as if it were gathered. As long as the downward line of that weight stayed inside the foundation area, the tower could stand. It was leaning, but not yet past the point where gravity would take over completely. For centuries, that balance held. The bells hung high in the chamber. Visitors crossed the square. Rain darkened the marble. Sunlight brightened it again. The lean grew slowly, almost too slowly for daily life to notice. Then, by 1990, the risk had become too serious. The tower was closed to visitors. Its angle had reached about 5.5 degrees. The top had moved several meters away from where it would have stood if the tower were straight. Modern engineers did not try to erase the lean. They understood that the defect had become part of the monument, so they reduced the danger carefully. They placed temporary lead counterweights on the higher side. They used cables as backups. They measured movements by millimeters. Then they used soil extraction, removing small amounts of earth from beneath the higher northern side of the foundation. This allowed that side to settle gently. The tower moved back by roughly 40 centimeters at the top. It reopened in 2001, after more than a decade of work. The result was not perfection. It was balance. The tower still leaned. It still looked like Pisa. But the danger had been reduced enough that engineers believed it could remain stable for at least another couple of centuries. That is the quiet beauty of the story. The tower was not saved because it had been perfectly designed. It was saved because accident, delay, observation, and science all became part of its path. Soft soil made it lean. A shallow foundation made the lean worse. Construction pauses gave the ground time. Modern engineering brought the tower back from the edge without taking away the shape that made it beloved. And now, in the Piazza dei Miracoli, the tower still stands over the grass. Its white marble catches the changing light of Tuscany. Its arches circle the leaning body in calm rows. Its bells rest high above the city. Below it, the old soil remains part of the story. Above it, the sky stays open and clear. The tower is beautiful, not because it is perfect. It is beautiful because it is still standing, held between failure and balance, between mistake and survival, between the soft earth below and the patient pull of gravity above.